Lesson 4.1 is moving into chapter 4, which is all about integration. And kind of the second world of calculus, the whole first half of the year we've been working on derivatives, so differential calculus. Now the second part we're going to move into integral calculus. And it's a very powerful operation, taking integrals, and you'll see their usefulness over the next couple chapters. So first off, I'm going to break this into 2 days. Day 1 is just going to be writing the general solutions to some differential equations. Second, using indefinite integral notation, and then some of the basic rules behind finding these antiderivatives. Antiderivatives and indefinite integrals are synonymous. They can be used interchangeably. Okay. Day 2, we'll find the particular solutions. So just looking at these green boxes here, if I ask you to take the derivative of the function provided there, f of x, you would of course say it's 2x, because we've learned that. What if I turned it around and gave you the derivative? So I'm telling you the derivative was cosine. Could you guess what the original function was? What is f of x? Well, a good guess might be sine, because we know if we take the derivative of sine, we come to cosine, right? So if I undo the derivative, I get back. The undoing of cosine takes me to sine. That's kind of the whole idea behind what we're doing today. You can see that I've got under the green here, over the green, four different equations. And if you just simply walk through and took the derivatives of each of these, you would get, what, 4x cubed on this one. 4x cubed, and the derivative of 6 would be 0. Here I get 4x cubed, and the derivative of negative 112 would be 0. And on this one, I would get 4x cubed. So I had 4 unique equations, but yet their derivative all turned out to be the same 4x cubed. That might present some problems, huh? Because I was just talking to you how we're going to back this up and say, okay, so what was the original function? Well, I can come up with the x to the 4th probably. I could be able to figure that out. But how would I figure out that it was 6? Or how would I find out it was plus 0? Or how would I find out that negative 12 existed? Or any number for that matter, some value c. That's where it gets a little tricky. So when I take and do the antiderivative, we are going to have to just talk about some general number, some constant, and we'll just do a plus c on it to account for these different values. Now there is a way to get the actual values, and we're going to do that tomorrow in day 2. But we must have a little bit more information provided to us. So keep that in mind. So we know that there are these cubics, or I'm sorry, this 4th degree. And this 4th degree may be just a little bit flatter than a parabola here. But there are many, 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 I want to infinite clone this. There are many, many different families of this same graph, right? I can do just some vertical translations, and that affects, maybe here's that x to the 4th, oops, x to the 4th minus 112, right? Down here at negative 112. So there are many, and all that this number does is play with the location vertical on that, vertical transformations, right? So we can get into the family, the shape of the graph, getting the actual one, how high it is, that takes a little bit more work. So the notion between derivatives and antiderivatives, not sure what happened there. The notion between derivatives and antiderivatives is they are inverse operations, much like multiplying, dividing, adding, subtracting. They undo each other. So when we created this line where all the functions turned out to be 4x cubed, the 4 equations I have written here, those are all antiderivatives for the function f prime equals 4x cubed, right? All of these would be examples of possible antiderivatives. Mainly the plus c, though, to be the most general of them. F of x is called the antiderivative of f prime of x. We get formulas for antiderivatives by reversing the differentiation rules. The term antiderivative is synonymous with an indefinite integral. So what is an integral? We've been talking a little bit around it. It actually looks like this is a symbol. So this is my integral symbol. It's an elongated S. It's kind of known as a summing function. It'll sum things up. F of x is known as my integrand. The dx will be present. It is the variable of integration. And then when I actually find this is my antiderivative. Our textbook makes use of the capital F a lot of times. So there's this integral of some function f of x, and we'll come out with capital F of x plus some constant. You could also think about it as being the integral of f prime of x to come back to my original function f of x, right? So one of the two ways is a good way of thinking of it. You know a lot of derivatives. That's what we spent the whole first couple months working on, finding derivative rules, utilizing those derivative rules to find derivatives. So I've mentioned many of them, the product one, or I'm sorry, the power one. The power came down, got that n out in front, and then we subtracted a power from it and had that n minus 1. Well, then you can imagine undoing this is going to involve adding back a power and dividing by this new power. So here I multiplied by n, so now I'm dividing by n plus 1. Because really this n was an n minus 1 idea, right? So if I add a 1 to it, I'm back to n, which is what I have here. This one had been reduced by a power of 1, so we're adding back that power of 1. Okay? So there's rule number 1, the power rule of integrals. The derivative sign was cosine, so the integral of cosine is going to be sine of u plus c. The derivative of cosine is negative sine, so the integral of sine is going to be cosine. And they're using u's, so I'm going to stick with the u's. Now, am I okay with my positive and negatives on this one? Double check your work. The derivative of cosine gives me negative sine, but yet I don't have negative sine, so I'm going to put a negative there, so I get negative of negative sine of u when I take its derivative. That'll bounce me back to a positive sine. So the integral of sine is negative cosine. The derivative of tangent is secant squared, so the integral of secant squared is tangent of u plus c. The derivative of e to the u is e to the u times u prime. They've been writing u prime as du dx all the way along here. That's fine, but we could write it as u prime if we wanted. The integral of e to the u then is e to the u. It is itself. It's both its derivative and its antiderivative. The one that isn't on here that I think would be worth putting on our chart, the derivative with respect to x of natural log x. Well, we know that is 1 over x. So if I integrated 1 over x dx, that would give me natural log absolute value of x, because we have to make sure this stays positive in order to have a domain that's defined, plus c. This integral could be written as x to the negative 1, couldn't it? Which explains, I'm not sure that you noticed this, but up in this power rule it said, hey, x can't be -1. This power can't start as -1 and then use this rule, the power rule. Because an x to the -1 has its own special integral. The antiderivative is x absolute, or natural log of absolute value x. Okay? Even if you tried here, you would, n cannot be -1. What would happen if n were -1? Well, I get -1 plus 1. Now I'm trying to divide by 0. That doesn't work. So there's a few special ones I pointed out. If you look on the second page of your notes, you're going to see a pretty nice set of the derivatives that you know so far, and then those integrals that accompany them. So the forward-backward idea here. Hey, there's one little typo. Please insert that n on the power rule for the derivative of x to the n. Okay, let's actually do this. Let's put it into motion here. Enough talk. Let's get some action. Well, one thing we can do, this 3 is a multiplier. We could pull it out front of our integral and say this is 3 integral of x dx. Now I'm going to employ the power rule of integrals. So this has a power of 1. I'm going to step up that power by 1 by adding 1. And then notice we have to divide by that same power, n plus 1. So it's a 1 plus 1 in this case because our n was 1. The 3 is just kind of along for the ride, plus some c. That gives me an answer of 3x squared divided by 2 plus c. I'm just going to write it as 3/2 x squared plus c. Can you check your work? Hey, great question. Why, yes, you can. If I take this and do the derivative on it, I should get back to the integrand. So 2 comes down, cancels with the 2. I reduce my power by 1, so a squaring goes to a first power, and the derivative of a constant is going to be 0. We notice those 2's canceled, and we get 3x. Beautiful. So it worked. Next problem, we just have 8. Well, the 8 could move out front if we wanted. Then I have the integral of dx. Well, that's kind of interesting, isn't it? So the integral of dx, I'm going to move that over because I have a purpose for that. I could think of this as x to the 0 sitting in here. Or a lot of people, I know what a lot of people said in class, hey, there's a 1 sitting there. And I said, yep, absolutely. But that 1 I could also think of as x to the 0, couldn't I? X to the 0 is 1. Now I got to add a power to that. And that's going to disappear on me, but that's okay. Now we've got to add. So I've got my 8 out front, and I had x to the 0, and I have to add 1 to it. Plus some constant. What does that get me? 8x divided by 1 plus c. So 8x plus c. Quick check back. If I take the derivative of this, I get 8, don't I? Perfect. That was the integrand. Forwards, backwards, easy, easy, easy. All right, this one looks hard, but as long as I have nice individual, like a polynomial, adding and subtracting, I really can think of these as individual integrations. So I can really think of this as 3 individual integrations. So let's take and do this one. The first one here, x raised to the 3rd, because I added a power. Now I have to divide by that new power. Minus 3, add a power. It was a 1, so now it's going to climb up to a 2. Divide by 2. Plus 4. I don't have any x, or I do have an x, but it's to a 0 power. Add a power that brings on an x to the 1st. I would divide by 1. Plus c. But it's not really necessary to write that 1 there, so there's my answer. Check out each of their derivatives. Does it bring you back to the integrand here? I suspect it will. Some of them can get a little bit more difficult. So I think I might want to rewrite this. Remember when we started derivatives? If we had something funky, we like to rewrite it. The same is true with these integrals. So I'm going to say that my function, my antiderivative, will look like the integral of x to the negative 3 dx. Now I can add my power. So if I start adding these powers, I'm completing the process of integrating, which is what this tells me to do. So I no longer write my integral symbol. So I'm going to have negative 3 plus 1 divided by negative 3 plus 1. Add on our constant that could be present, and let's simplify. F of x equals x to the negative 2. You know what, I'm going to write it x to the negative 2 divided by negative 2 plus c. But often we do not like to leave our functions with negative exponents. So I'm going to drop that x to the negative 2 down below and write it as an x to the positive 2. So I got 1 over x positive 2, a 2 in the bottom right there, and this negative I am going to put up on top, and then don't forget to go our plus c. So I get negative 1/2, negative 1 over the quantity, 2x squared plus c. This one, I will have f of x equals the integral of x to the 1/2 dx. Add a power. Our f of x is going to look like x to the 1/2 plus 1 divided by 1/2 plus 1 plus c. I need 2 more spots, okay? I'll switch it up here. That's going to give me an x to the 3/2 divided by 3/2 plus c. But dividing by this fraction is like multiplying by its reciprocal, so I'm going to have 2/3 x to the 3/2, almost said it wrong, plus c. There's how I'd like you to format your final answer. So at the moment that I started adding powers, right? I added 1, I divided by that new power. That's when I drop the integral symbol because I no longer need to continue to antiderivative it. This last one's actually going to be pretty easy. We've worked with some of these before. So our function will be, I'm going to move my 2 out front. So 2 integral sine of x dx. The integral of sine. Okay, whose derivative is sine? Well, that would be cosine, but the derivative of cosine gives me negative sine. Oh, that's right. The integral of sine is actually negative cosine. So I need a negative cosine x. And that's really the final answer as well. Not much to simplify there. Just make sure you have that negative sign out. Is it okay? You know, as I was doing this, I said, okay, I got the 2, and then I've got negative cosine x. Oh, I forgot my plus c. Is this the same as this? Well, I know what you intended. You intended it to be times. But if you don't put in those parentheses, what does it end up looking like? It looks like 2 minus cosine. The safer route, just go ahead and put that negative right out front. As you said, the derivative or the antiderivative of sine is negative, and then go write your cosine after that too. There are a few more tricks that will help you as you integrate. Trick number 1 is that rewriting, which we just practiced a little bit. Trick number 2 might be to multiply things out or distribute. Sometimes, you know, that might involve foiling the first times the outer times, or first times first, outer times outer, inner times inner, that sort of idea. Sometimes you might want to separate the fraction. So just a few hints. I see a squaring. This presents problems. What we love polynomials in so many ways, right? They're so easy to take derivatives of, and they are much easier to take integrals of rather than some function raised to the second. So can I get this into polynomial style? You bet I can. So that's kind of integral. 3x minus 1. If you don't trust yourself doing this mentally, write it down, right? 3x minus 1 times 3x minus 1. Okay, now let's FOIL it. Our function will equal the integrand. Once I get this FOILed, which would be 9x squared, a negative 3x for a total of negative 6x in the middle, plus 1 at the end. All of this multiplied by dx. Now I can actually go into the process of the power rule for integrals. Let's add power it up. So we're going to go 9x squared plus 1, which would give me a 3, and then I can divide by that 3. Minus 6, x to the 1 plus 1, oh, that became 2, so now I'm dividing by that same power 2. Plus 1, bring on an x, since it wasn't there, plus c. Simplify this, I'm going to get my antiderivative is 3x to the third minus 3x squared plus x plus c. Do a quick check. Can you take the derivative of that and get back to, probably don't want to match to this, but this would be a better way to match. It's equivalent to 3x minus 1 quantity squared. But yeah, I think you'll find out it works. B looks horrendous, doesn't it? We have a rational function. Keep in mind, you know, the more I can get into a polynomial, the more I love it, because those are pretty easy to take integrals of. So can I make this look more polynomial style? Yeah, I think I can. So I know many students favor this method, which is fine. X squared plus 4x. They take their numerator and rewrite the denominator as x to the negative 5, right? dx. That works perfectly fine, and then we'll take and distribute. I do find people make a ton of mistakes on this, but if you can do it, it works. That'll give me the integral of x to the 2 plus negative 5 plus 4x to the first plus negative 5 plus 5x to the negative 5 dx. When I have the bases the same and they're multiplying, base is x, and they're multiplying, I add up their exponents. So I haven't integrated yet. All I'm working on is simplifying out this rational function that we started with. A lot of work beforehand makes the integrating easier. Do the algebra before you start attempting to integrate. All right, I think we're good there. We got x to the negative third, 4x to the negative fourth, 5x to the negative fifth. Now I can go into the add a power routine. So since I'm actually in the act of integrating, I'm going to drop the integral symbol. So I'm going to add a power. That'll take me to negative 2. I'll divide by that new power, negative 2. I have been integrating for years, and you know what? I still tell myself, add a power, divide by the new power. Add a power, divide by that new power. Try it. It's effective. It'll get you the right answer as long as you're adding one right. Rewriting this so that we don't have a negative exponent sitting in our answer would create 1 over x squared. And my 2 out front here, the negative, I'm going to shift it up front. Negative, so this will be a subtraction. 4 stays on top, 3 on the bottom. X to the third will be written below, so moving the negative exponent to the bottom. Still have a negative fraction, so I have negative or minus 5 over 4, oops, right, a 4, x to the fourth plus c. There is our answer. So we made it easier. Now, I talked about this as one possibility, rewriting that x to the negative fifth and distributing through. That works great. Another option is these are ones that I absolutely love, rational fractions of this nature, that have this single term in the bottom, because it allows me to write this individually and it actually be helpful. Would it have been as helpful, I'm going to go that disappearing ink, if this had been 5x squared plus 1? And no, then I don't see the benefits because I can't simplify my fractions. But with just this solo denominator, smooth work now. 2 minus 5, I have more powers, more x's in the bottom. So that's going to be an x to the negative 3, 4x to the negative 4, 5x to the negative 5, dx. Same place that we were before when we wrote this as multiplying by x to the negative 5 and processed it through. We both came to this conclusion, and then now it's integration technique from there. So if that's your favor, go with that. I love doing it that way. Okay, C should be pretty easy. Do you see a fraction coefficient? I do. So I'm going to pull my 3/2 out front so I can just focus on my cosine integration. So I could say my integral is going to turn out f of x equals 3/2 integral of cosine theta d theta. The integral of cosine, well, whose derivative gave me cosine? Oh, that came from sine, didn't it? Check your work. Can I take the derivative of sine and get cosine theta? Yes, perfect. 3/2 comes along as a multiplier. That one is done. Okay, D is a fun one. Probably take us a couple minutes, and that's all that's going to be on this first video. So remember how we love polynomials. Can we kind of get to a polynomial state? Yeah, I think so. I would distribute on top, multiply that out, and then I would do that division step next. Okay, so let's take it in that order. Our function is going to be first times first gives me 6x squared. I pick up 8x, a minus 9x, and a minus 12 all over x to the 1/2. Rewrite that a bit. Okay, there's a little bit of simplifying up on top before I start doing the division step. I get negative x and a minus 12 over x to the 1/2. Well, remember, your teacher loves these, so I'm going to do it in that technique of writing them, thinking of them as over. So I'd have 6x squared over x to the 1/2 minus x to the first over x to the 1/2 minus 12 over x to the 1/2 dx. You probably think, does that really serve much purpose, this dx out at the end? Right now, just think of it, it's informing us what we're integrating with respect to. There is a purpose for it, and you're going to see it when we get into Riemann sums and things like that. You're going to appreciate it. All right, still a little more simplifying, right? Still more simplifying. 2 minus 1/2 is x to the 3/2. 1 minus 1/2, this is just purely algebra exponent rules. 12x to the negative 1/2 multiplied by dx. If you get good algebra skills, you're going to make an excellent calc student, right? Now let's do the integration. And since I said I'm going to integrate, I can drop my integral symbol. All right, add power time. 6x to the 3/2 plus 1. That's like a 2 over 2. Oh, that's 5/2, so I'm going to be dividing by 5/2. Minus x to the 1/2 plus a 1. That's a 3/2, so that's a division by 3/2. Minus 12 x to the negative 1/2 plus 1. That's a 1/2, so that's a division by 1/2. Squeeze in our plus c. Plus our constant. All right, what can I do with this mess? Well, dividing by fractions like multiplying by reciprocals. So let's just kind of note we're going to multiply by reciprocals. That's our next line here. So I'm going to have 2, it doesn't even look like a 2, 2/5 of 6 x to the 5/2 minus 2/3 x to the 3/2 minus 2 over 1 times 12, probably could have done that right then. X to the 1/2 plus RC. Final steps. 12/5 x to the 5/2 minus 2/3 x to the 3/2 minus 24 x to the 1/2 plus c, leaving it with fractional exponents just fine. You don't have to write them as radicals. There's our answer. Holy buckets, what an ugly answer. Would you have guessed its derivative is this? Wow, huh? That's pretty crazy. All right, so your homework is to do this worksheet. I printed it out for you, but those are the problem numbers out of your textbook, so you can check there. Make sure you look at the odds. These ones that are in pink, remember, connect to it being done on a video, so if you'd like to see that, go ahead. Good day.